Hey everybody, this is Professor Ross, and in this video we're going to talk about comparing two means with a theory-based approach. Let's take a look at some notes here. We want to be able to compare two means, which means we've got two groups established by a binary categorical explanatory variable. And we're comparing their means, which means our response variable is quantitative. So we've got two variables, an explanatory and a quantitative variable. And we've looked at how we can examine those with a simulation-based approach in order to do statistical inference. Now we'd like to be able to do inference with a theory-based approach as well. Our key learning objective throughout this is to be thinking about how we're using the logic of statistical decision making. And here specifically to decide, do we have some different means in our two groups, or are the two means the same? As I mentioned, we've talked about how to do this with a simulation-based approach, and I want to contrast that to a theory-based approach. For simulation, we need shuffling to simulate division into our response categories, and that takes a lot of work to do by hand, so we really need computing power in order to accomplish that. And so simulation-based approaches have really taken off more recently as computing power has become more ubiquitous and able to handle larger and larger sets of data. In the past, people have used a theory-based approach because it was not so computation intensive, and under the validity conditions, we could reach the same objective, come to the same conclusions. So for a long time, people have used a theory-based approach. It's good for you to know about it. And also when we when we have large sets of data, a theory-based approach can be the right choice because it gives us the same answers as a simulation, and it won't bog down the computer when we have a large set of data. We'll take a look at an example of one like that today. The theory-based approach uses the central limit theorem. So it's the same theorem we've looked at all along, and so it gives us the same kind of information. It basically predicts what the simulation would tell us should happen with the null hypothesis. We do need to meet a validity condition, and this is our fourth validity condition. So you got to know what scenario you're in and match the appropriate validity condition. When we have two means that we want to compare, in other words, a categorical explanatory and a quantitative response, then our condition is we have to have a sample size of 20 for each group. That means here we're going to have at least 40 total, 20 in each group or more. And then both samples need to be somewhat kind of not too strange. We can't have strong skew or heavy outliers in either of the groups. Once we know that we meet this condition, it's big enough and it's not very strange, then we know that we can use a theory-based approach, which is a lot less computational heavy and therefore can be nice when we have large samples. I want to show you a few of the details here. I don't want you to get intimidated by these formulas. I'm not going to ask that you use these formulas by hand. Very few statisticians even do any of this by hand anymore, mostly through technology. Why am I showing it to you? Because I want you to see the main way that that all of this is really the same structure as what we've done all along. So this is when we have an explanatory binary variable, categorical binary variable, and our response is a quantitative variable. Our parameter is the difference in the population means, mu1 minus mu2, and 1 and 2 are the two groups set up by the binary variable, and the means are the mean of the quantitative variable. And our statistic mirrors that parameter. It's what we see in the sample. Instead of the mean of the population, we have the mean of the sample. So x bar 1 minus x bar 2. The theory-based approach formulas for our statistic of a difference in sample means, we can look at a standardized statistic, we call it a t, and this formula is really the same as we've had all along for standardized statistics. So we have our statistic, which in this case is x bar 1 minus x bar 2, minus the mean of the null distribution, which in these is always 0. So we don't even write minus 0 down generally. And then divided by SD, the standard deviation of the null distribution, or an approximation of that, the SE. So That's the same structure as always for the standardized statistic. As I said, I'm not going to ask you to calculate that by hand, but knowing that it's the same structure means it has the same interpretation. It still tells us how many standard deviations from the claim of the null hypothesis, the mean of the null distribution, did our result end up being. We also have a formula for the confidence interval, and this also has the same structure, so it's going to end up with the same interpretation. We have our statistic plus or minus what's called the margin of error, a multiplier times the spread of the null distribution. And so that's the same structure as always, and we interpret a confidence interval in the same way as always. We feel confident that the true parameter, that the true difference in means, will fall somewhere inside that confidence interval. Instead of doing it by hand, we'll use technology and especially the theory-based inference applet. So let's try that out with an example. Does breastfeeding babies increase intelligence? Some people have concerns about not breastfeeding babies, instead feeding them with formula. And so we can study that. And a research group gathered data on breastfed babies and not breastfed babies, and just found out, from mothers that reported whether they're breastfeeding or not breastfeeding, and they got 237 breastfed babies and 85 not. And then when they got old, or they found out whether they were as children, and then they tested their IQs when they're old enough to do an intelligence test. And so they found the mean IQ for the breastfed babies and for the not breastfed. And they also found standard deviations for each of those. Whoops, sorry. So we can take a look at this, and what would be good to start with is to create graphs with a multiple means applet. That's where we did the simulation-based approach, and it creates some nice graphs for us, so we're going to start there. However, we're not going to continue there because we have a relatively large sample size. We have well over 20 in each of these, and we'll find out we don't really have concerns about doing a theory-based approach. And if we tried to do a simulation with such a large sample, we'd find out that the simulator would get bogged down pretty badly. So using a theory-based approach is going to be the better approach here. On the applets page, that data is down below in chapter 6, and I just grabbed it and I went to the multiple means applet and popped that data in here. And you can see what we've got here. We've got dot plots of each of them, and they're both relatively spread out with a few higher and lower, but not a real strong skew in either direction, and no real strong outliers, maybe a little bit of an outlier here. And also we can see overall that the bulk of the data and the means of the data are really not too far apart. So our not breastfed babies, maybe slightly lower median there, and our breastfed maybe slightly higher, but both relatively even spreads there. We can also take a look at their means. Once again, those match what we saw in standard deviations. Now, as I mentioned, this is where we could do a simulation-based approach, but with a total sample of 322, that's getting kind of large for our simulator to handle very smoothly. So instead, I'm going to jump over to the theory-based applet, theory-based inference, which I had pulled up here. And here we can enter our data and do a theory-based approach with relatively little computational power. So how do I do a theory-based approach with comparing two means? Well, I certainly don't want to look at one proportion. So the first thing is figure out what scenario I'm in, and I'm going to be comparing two means. That'll change the information I put in here. And so now what I need for each group is their size, their mean from that group, and the standard deviation from that group. I'm going to go ahead and use the breastfed group as group 1, 237 and 105.3 and 14.5 was it? Let's just got to copy my data in there. There we go. 14.0, 100.9. And this was my smaller group of just 85. This applet does give us a graph. Unfortunately, it's not that useful because it can only do so much with the summary data. So it does show us the means look a little bit different and kind of the typical spread. But I don't think this graph even has a name. It's just kind of a visualization of this, and it's not all that useful. What we do want to do is a test of significance. Let's go ahead and check that. And by default, it's always going to have the right null hypothesis that the two means are the same. They have no difference. Uh, the alternative, we can decide, do I want less than, greater than, or not equals? And the default we want here is not equals. You can see here the less than is probably not the right choice, but the greater than I would have to justify coming in saying somehow I had the feeling or I knew that breastfed babies were more intelligent. And that seems a little suspicious. I think here just coming in saying, I don't know, let's just find out if there's a difference is the more fair approach. So a two-tailed approach. And here we get a t-statistic and a p-value just as usual with the theory-based applet. Let's interpret this. What's the t-statistic? 2.46. My result of a difference of about 4.4 in the intelligence levels is over just about 2.5 standard deviations away from a difference of 0. That's not very typical to see something 2.5 standard deviations away. In fact, we know that there's only about a 1.5% chance of seeing a result like ours or more extreme if that null hypothesis is actually what's going on. So if there really is no difference between these two groups, then it'd be really rare to see a result like this in a sample like we had. That's strong evidence against the null hypothesis. We're going to reject the null hypothesis. We do not believe there's no difference in the mean intelligence of these two groups. What seems to be the case, looking at it with a positive difference here, group 1 seems to have the higher average intelligence. That was my breastfed group. The natural follow-up question is, well, how much more intelligent are they? Is this something so big we're going to notice it? Is there going to be a meaningful difference? Or is it going to be such a small difference we may never notice it? The confidence interval can help us understand that. So we're going to check confidence interval. And here it is. I've got a 95% confidence that the parameter falls between these two numbers. Let's call it 0.8 and 8. What's the parameter? The parameter is the difference, here it is in the null hypothesis, the difference in the mean IQs of the two groups. So the difference between those mean IQs, somewhere between 0.8 and about 8. Now, as high as 8 points of IQ, maybe we'd notice that difference. But less than 1 IQ point, we're probably not even going to notice a difference that small. So that's the one I want to focus on, is the one that's closer to my null claim of 0. Pretty small potential difference between these groups, so small we may not even notice it. A couple other questions. Can we conclude that we have an association between the two variables? We can. We found a statistically significant difference. Breastfed babies have a higher mean IQ. Can we conclude cause and effect, that it must have been the breastfeeding that caused this to happen? Here, we got to be a lot more careful. We cannot conclude cause and effect. We have not done an experiment. We simply observed what these values were, asked the parents, did an IQ test and observed. We did not assign to the two different groups. In an experiment, we'd have to do random assignment to our two groups. We do not randomly assign parents to either breastfeed or not breastfeed their babies. And so therefore we can't conclude a cause and effect. So that's how we can do a theory-based approach when we want to compare two means.